So now that we have looked at an ideal Bose gas, confined Bose gas, we will take up the final example in this system. So what we want to look at is the ultra-relativistic Bose gas, where my epsilon, the energy is given by C times P, which is h bar C K. And I start with the partition function ln q eta. The general expression was minus eta sum over k ln 1 minus eta z e to the power minus beta epsilon. Now here eta is plus 1, eta is equal to plus 1 for a bosons. So I have q plus is going to be minus sum over k ln 1 minus z e to the power minus beta epsilon. The sum over k, as usual, is converted to this density of state as v over twice pi whole cube integral k square over dk in 3 dimension. And since I have this expression, I can write down dk as d epsilon over h bar c, so that I have v over there has to be a gv here and a 4 pi over here. We will substitute the value of g a little later. Let's keep it 4 pi times gv divided by 2 pi whole cube, and then I have integration of d epsilon over h bar c, and I have h bar c square in terms of replacing k. Sorry, this has to be epsilon square over h bar c whole square, so that I have 4 pi gv divided by 2 pi h bar c whole cube integration d epsilon square, which gives me 4 pi gv divided by hc whole cube integration d epsilon square, so that the density of state we will straightforward write down as 4 pi gv hc whole cube epsilon square. Now this means that ln of q plus is going to be minus integral, let's write down the factors. Okay, so d epsilon g epsilon 1 minus z e to the power minus beta epsilon log of this, which is going to be minus 4 pi gv over hc whole cube d epsilon square ln 1 minus z e to the power minus beta epsilon. We carried out these integrals. The way to go ahead is to use integration by parts, and we will do it over here also. This is epsilon cube by 3 ln of 1 minus z e to the power minus beta epsilon 0 to infinity. This is 0 to infinity minus, I am going to have integration d epsilon cube by 3. Derivative of this log is going to give me z e to the power minus beta epsilon minus z e to the power minus beta epsilon, and then dd epsilon of minus beta epsilon, which is going to give me a minus beta factor, so that this minus and this minus is going to make it a plus, and this minus and this minus is going to make it a plus, and I know that this first term is going to vanish. I'm going to have 4 pi gv hc whole cube beta over 3 integral 0 to infinity d epsilon cube z inverse e to the power beta epsilon minus 1. This is ln of q plus, and I know that beta pv is going to be ln of q plus which is going to be 4 pi GV HC whole cube beta over 3 0 to infinity d epsilon cube z inverse e to the power beta epsilon minus 1. The total energy is going to be G epsilon d epsilon and epsilon divided by z inverse e to the power beta epsilon minus 1. We have seen it several times because this follows from the relation that total energy is sum over k epsilon k and k. This gives me 4 pi GV HC whole cube integration d epsilon. G epsilon behaves as epsilon square and I have an additional epsilon factor here, so this gives me epsilon cube z inverse e to the power beta epsilon minus 1. Now if you turn your attention to photons, something is very, very special. So what you see over here, that for low excitations like photons, the chemical potential mu is equal to 0 because it does not cost you energy to create particles at epsilon equal to 0. Right? So once mu is equal to 0, this implies that Z is equal to 1. So essentially, the thermodynamic pressure becomes 4 pi G. The volume factor cancels over here, the beta factor cancels over here, HC whole cube 1/3 0 to infinity d epsilon cube e to the power beta epsilon minus 1, and I can substitute for this 0 to infinity d of beta epsilon divided by beta epsilon whole cube 1 over beta cube e to the power beta epsilon minus 1, so that the thermodynamic pressure I can write down 4 pi G over HC whole cube kBT raised to the power 4 by 3 0 to infinity dx x cube over e to the power x minus 1. Now the value of this integral I know. The value of this integral is zeta 4 times gamma 3. Am I right? Sorry, this has to be gamma 4. Because I know from our earlier discussion that Fm plus of Z is 1 over m minus 1 factorial dx x to the power m minus 1 Z inverse e to the power x minus 1, and gamma of m is going to be m minus 1 factorial. So essentially I multiply this by gamma 4 and divided by gamma 4, and I realize that this quantity that I see over here is equivalent to F4 plus of 1, which is zeta times 4, so that the thermodynamic pressure is 4 pi G HC whole cube kBT raised to the power 4 gamma 4 zeta 4. You should know that gamma 4 times zeta 4 is pi 4 over 15. We will later on use this one. Now the internal energy it follows is 4 pi GV HC whole cube. Once again, if you look at the structure of this internal energy, I am going to have 0 to infinity. So I have always missed out this integral limits. So please note that they always run from 0 to infinity. D of beta epsilon, the standard trick is apply over here, 1 over beta cube e to the power beta h epsilon minus 1, and that is going to be 4 pi GV over HC whole cube kBt raised to the power 4. Again, it's going to give you gamma 4, zeta 4. So if you compare this expression over here and the last expression over here, you see that U by V, I have missed out a factor 3 over here. 1/3 of U by V is the pressure, which is the case for an ultra-relativistic gas, which we have done several times in this course. Additionally, you must note that the pressure goes as T to the power 4 and U goes as T to the power 4 in this case. Now that I know the energy density, even I can write down U by V, the energy density goes as T to the power 4. Now suppose I have a container which has a tiny hole, and this is filled with photons, so that these photons come out from this hole. So essentially what I'm trying to look at is what is called a black body radiation, right? For this, I want to write down epsilon as h bar omega. So I started off with K, I went to G epsilon. So G of K, the density of states, and from this I want to go to G of omega. So G of epsilon was 4 pi GV divided by HC whole cube, and then I had epsilon square. So that this sum over K I had, it was equivalent to 4 pi GV over HC whole cube integration epsilon square d epsilon. Don't forget that. Now epsilon is h bar omega, and therefore d epsilon d omega is going to be h bar. So this becomes h bar d omega, and this becomes h bar square omega square, so that this is 4 pi GV over HC whole cube times h bar cube omega square d omega, which is equivalent to 4 pi GV divided by, I have h cube c cube and 2 pi whole cube. This is the part which follows from h bar. So that, and then I have omega square d omega. This becomes 4 pi GV. The h cube cancels out, c cube 8 pi cube. This is 2, and I have pi square. So I have GV over 2 c cube pi square integration omega square d omega. So that the density of state in the frequency spectrum is equivalent to GV over 2c cube pi square omega square. Now for a photon, the degeneracy factor is 2, so that I can write down this as V omega square over c cube pi square, a very nice expression for this density of state, right? Therefore, it follows that the number of oscillators within a range of frequency between omega and omega plus d omega is going to be d of n omega, which is going to be average of n omega, g omega, d omega. And average of n omega I know is e to the power beta h bar omega minus 1 because z is 1. G omega is v omega square c cube pi square times d omega. So one has dn omega d omega as v omega square over c cube pi square 1 over beta h bar omega minus 1. This part, the one in the bracket, essentially follows from this average of n omega, which I know average of nk is 1 over z inverse e to the power beta epsilon minus 1, and z is 1 for a photon gas, epsilon is h bar omega, so I have this expression, right? Now I can bring the volume in the denominator so that I have 1 by v dn omega d omega is going to be omega square c cube pi square 1 over e to the power beta h omega minus 1. Correct? Let's see look at the left hand side. N by v is the number density, small n. So therefore the density of oscillators which are between, so density of oscillators which are between omega and omega plus d omega, which has frequencies between omega and omega plus d omega, is dn omega. D omega is given by this expression, omega square c cube pi square 1 over e to the power beta h bar omega. Good. Now I want to calculate the amount of energy that is contained within this frequency interval. So now I want to know the energy density contained within this frequency interval omega and omega plus d omega. So one can also write down du of omega, which is the amount of energy which is contained within that, is going to be epsilon omega average of n omega, g omega and d omega. Epsilon omega is h bar omega and n omega is 1 over e to the power beta h bar omega minus 1, and then you have g omega, which is omega square c cube pi square d omega. There is a v factor over here, omega square v. So that the energy density, so 1 by v du of omega is going to be h bar c cube pi square omega cube divided by e to the power beta h bar omega minus 1. So clearly this means that the energy density small u of omega, where small u is defined as capital U divided by v, the density divided by d omega is going to be h bar c cube pi square omega cube e to the power beta h bar of omega minus 1. Now one has to go back to the original problem and look at this, that I have a box which is filled with photons and I have a tiny hole here from which the photons emerge. So I want to know the flux, and the flux, if these photons move with a velocity c, the flux is going to be n over 1/4 n times c, right? Where it is understood that this is going to be n omega times. So now this is the energy density. So if you want to ask what is the amount of energy which is contained within a frequency interval omega and omega plus d omega, the answer would be du d omega times d omega. And similarly, the number of oscillators you have within the frequency interval omega and omega plus d omega, you have dn d omega times d omega. Now the original question that we wanted to ask was that we had this problem where we have a box and there's a small hole from which photons are coming out, right? So this is the radiation, black body radiation, which you're looking at. So I want to know the energy flux, correct? So here, this is the classical problem of effusion, and the answer to that is the number density, the number flux is going to be average V divided by 4 times N. This is for the classical result. In our case, we adopt this relation and identify that we are looking at the frequency interval omega and omega plus d omega, and therefore we have number of oscillators which is d and d omega, and each of these oscillators carry an energy h bar omega, which we have already identified. Therefore the energy flux du d omega, so we will write down this as the energy flux that's coming out of this small tiny hole is going to be h bar omega. Sorry, the average velocity is the velocity of light, which is c by 4, and I have dn d omega. This is per frequency interval, right? So this is per frequency interval. Once again, if you want to know how much energy is coming out within this, so let's say delta E is going to be C by 4 H bar by omega dn d omega times d omega. This is the amount of energy which is coming out within a frequency interval of omega and omega plus d omega, which we write down as C by 4 H bar omega, and then I have dn d omega, which we had before, which was this expression becomes omega square c cube, and I have pi square 1 over e to the power beta h bar omega minus 1, and this gives me omega cube over, okay, so first we write down as h bar, one factor of c cancels with one factor of c to give you c square, so you have 4 pi square c square, and then you have omega cube, this omega and this omega square here, and then you have e to the power beta h bar omega minus 1. So if you were to measure the amount of energy contained which is coming out of this tiny pore within a frequency interval of omega and omega plus d omega, then you will see that this is the total amount delta E times d omega. So we will write down dE instead of writing a delta, we will write down dE. Hence the total energy throughout the whole spectrum is going to be E, which is going to be h bar 4 pi square c square 0 to infinity d omega omega cube e to the power beta h bar omega minus 1. If you substitute beta h bar omega is equal to y, or let's say x, this would be a preferred choice, then you see d omega is going to be dx over beta h bar, so that you have h bar over 4 pi square c square integration 0 to infinity dx over beta h bar, and you have x cube over e to the power x minus 1 over beta h bar whole cube, which gives you h bar 4 pi square c square 1 over h bar raised to the power 4. You will have beta cube 0 to infinity dx x cube e to the power x minus 1. This is once again familiar to us. This is gamma 4 zeta 4. So that you have this expression, the total energy which is radiating out of this hole is going to be 1 over 4 pi square c square h bar cube kBt raised to the power 4 gamma 4 zeta 4. And this is sigma t to the power 4, where sigma is going to be kb raised to the power 4 divided by 4 pi square c square h bar cube times gamma 4 zeta 4, which is going to be pi 4 over 60, and then you have kb raised to the power 4 pi square h bar c whole cube, so that you have pi square kb raised to the power 4 divided by 60 h bar c whole, no sorry, this is wrong here. So this is going to be h bar cube c square h bar cube c square. This law that you see over here is called the Stefan Boltzmann law. And this constant is called Stefan's constant. One can plug in the values of kb, h bar and c to determine its value. As a concluding remark, we come back to this expression. We come back to this expression that we have over here, and we look at, so we have dE, which is going to be h bar over 4 pi square c square, and then I have omega cube e to the power beta h bar omega minus 1 d omega. Now if beta h bar omega is much larger than 1, we have this as dE, which is going to be h bar over 4 pi square c square omega cube e to the power minus beta h bar omega d omega. In the opposite limit, when beta h bar omega is much less than 1, I can expand the exponential over here, and that gives me dE is going to be h bar over 4 pi square c square omega cube divided by beta h bar omega. To the leading order, the h bar cancels out, and of course you have a d omega over here, which is going to be omega square over 4 pi square c square times kBt d omega dE. And this is the expression that you get when beta h bar omega is going to be much less than 1. This is what is called what is known as the Rayleigh-Jeans law, and this is called Wien's law in radiation. So with this we conclude this section.